recording. Yeah. It's up there with keyboard error. Press any key to continue.
I had my keyboard set to the UK standard on my
Oh, fun.
this morning. Couldn't figure out why I was getting
You can't
symbols.
can't put comments in your bash scripts.
No, I couldn't. Couldn't do the tilde key either. That wouldn't work.
Yeah. Awesome. All right, so let's talk about PA3. You don't have to start this till Friday technically, but since we don't meet on Fridays in general, I wanted to introduce it at least today. And some of this later section won't make sense until we talk about using linked lists to implement queues. But let's go through the basics of this, and I'll show you what the program should do. So PA3, you're working with stacks and queues, okay? And you're going to implement these using linked lists, not arrays. I've always had students use arrays for this in the past. I think linked lists make sense because that's where we're heading, so we're going to use that approach. First comment, try to stick to this idea of an abstract data type, okay? A queue is something which you can initialize, add to the head, add to the tail, remove from the head, see if it's full, see if it's empty, print the contents of maybe, and that's it. And your main program should interact with your queue by calling these functions. Okay, don't put code in your main program that says if tail plus 1 modulo 1000 equals head, right, or things like that. That's details that belong in this level below the firewall, right? So try to stick to that as much as possible. So what does your program do? You run your program and it's going to create an empty stack and an empty queue. It's going to maintain these two structures independently of each other for the life of the program. So you're going to have a stack, you're going to have a queue. They're totally separate from each other. Nothing you do to the stack should affect the queue and vice versa. Okay, don't try to mingle it all together into a single structure, two of them, all right? And then you have a really simple command line interface. You can use the command S, Q, P, uppercase Q, or you can type in a number. Those are the only things your program will understand. So the program can operate in one of two modes. It can be in stack mode or it can be in queue mode. And if you're in stack mode, everything that you do is related to the stack. If you're in queue mode, everything you do is related to the queue. So this saves us from having a print queue, print stack, add to the queue, add to the stack, remove from the queue, remove from the stack, right? So you're in one mode or the other. And you can switch back and forth by using the S and the Q commands. S for stack, Q for queue. All right, additionally, whenever you use the S command, you should print the current contents of the stack. Even if you're already in stack mode, if you say S, print the contents of the stack. And I'd like the stack printed on one line with spaces in between each number. And I want the top of the stack on the left. Okay, so top of the stack and then the deeper numbers in the stack all the way to the bottom of the stack. For a queue, you want to print the same thing, print the contents on one line separated by spaces. The head of the queue goes on the left. Deeper into the queue, and then the tail of the queue is all the way on the right. And these are stacks and queues of integers, right? Just like we've been talking about. All right, if you type a legal number, 15, -6, whatever, you're automatically asking that that get added to your data structure. If you're in stack mode, push it onto the stack. If you're in queue mode, insert it into the tail of the queue. And then if you use a P, that says either pop from the top of the stack and show me what that value was, or remove from the head of the queue and show me what that value was. So you insert by just typing a number, you remove by using the P command. And whether you're inserting or removing from the stack or the queue depends on which mode you're in. So pretty pared down set of interactions that are possible. And then an uppercase Q quits the program. So let me show you the behavior. So I run PA3, it gives me a little help message, it gives me a welcome message, and then it shows me the basic usage. Okay, that's up to you whether you want to do that in the beginning or not. But if you type something it doesn't understand, you should get the same help message, right? Something that tells you what the legal commands are. So I can pretend that a question mark gives me help, but actually anything it doesn't know will give me help. All right, so I'm going to do an S, which puts me into stack mode. It tells me it's switching to stack mode, and it tells me my stack is empty. There's nothing to print. If I say S again, it'll do exactly the same thing. Okay, let's push a number on the stack. What number should we push? 5. So we've pushed a 5 on the stack. If I want to see the contents of the stack, just say S. There's the top of the stack. It's got a 5, nothing else in there. If I push a 7 and I push a 9 and I look at my stack, 9 is the last thing I pushed. That's the top of the stack. 7 was the previous thing. 5 was the first thing. That's all the way at the end of the stack. So I can push a bunch of more things onto the stack and my stack grows. Now if I start popping off, what's the first thing that should be popped from the stack? 23. So I can say pop, there's my 23. If I look at my stack, the 23 is gone. If I push a 24, that's at the top of the stack now. And if I say pop, the 24 comes off first. If I say pop again, I get my 19, and then my 17, and then my 13, and then my 11, and now my stack just has those first 3 things that I pushed. The 5 is never going to come out until I pop everything that I added after it. Right, so that was the first thing in, it's the last thing out. All right, I can switch to queue mode by using the queue command, and now it shows me my current queue, which is empty. So the head's on the left, tail on the right, and there's nothing in between. So let's insert a 2, and if I look at my queue, I've got a 2. And that's the only thing in the queue. If I insert a 4, and I look at my queue, I've got a 2 and a 4 in my queue. 2 is still the head, 4 is the tail. So I can add a few more things to my queue, and now it's got a 2, 4, 6, 8, 10. If I say remove, which is P, what's the first thing it's going to remove? It's going to remove the 2, right, because that was the first thing I added. And now if I look at my queue, I've got the 4, 6, 8, 10. All right, I can go back to stack mode. My stack is still there. It's still intact. Nothing has changed. Okay, I can go back to queue mode. My queue is still intact. Totally separate. Let's go into stack and let's add some more things. Let's go back into our queue and let's add some more things. And they're both totally independent structures. So my stack, I should be able to pop 6 things off. And now my stack's empty. If I try to pop one more thing, it should give me an error. Stack is empty. Don't blow up, don't seg fault, don't delete all my files, right? Just say stack is empty, but keep accepting commands, and don't disturb your queue. Okay, nothing in stack mode should affect your queue and vice versa. So I can go to queue mode, that's still intact. I can start popping things off until I get down to the 13. Now my queue is empty. If I try to remove one more, tell me the queue is empty. Straightforward looking, behavior-wise, yeah.
What happens if you start your program and you hit a number without selecting?
You got to kind of decide what mode you're going to start in, or you could give an error message and say pick a mode first. I'm fine with either. I think I default to stack mode. Yeah. But it would be totally fair to say, like, please select a mode. All right, so I'll leave that up to you.
So for this setup that you chose,
Mm-hmm.
it would probably be wise to then say, like, welcome, blah, 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 you're in stack mode.
Yeah, yeah.
And then,
Yeah, so if you're going to make a default, it would be good to let them know they're in stack mode. All right, that's really all the program does. Okay, lets you put things in, lets you take things off. So my stack's empty, my queue's empty. If I put in 1, 2, 3, and then I switch to queue mode and I put in a 1, 2, 3, right, I've inserted in the same order. My stack stored these things 3, 2, 1. My queue stored them 1, 2, 3. That's the essential dualism between stacks and queues, right? The stack basically reverses the order. And this is part of why I'm asking you to put top of the stack on the left, head of the queue on the left, so you can mimic that behavior. All right, when you're done, quit. Free all your memory before you quit. I didn't free my memory, so I can't demonstrate that. All right, so that's the basic behavior of PA3. So your stack you want to implement with a linked list. I want your linked list to still have a sentinel node. I'm probably not going to take off points if it doesn't. But if it doesn't have a sentinel and it doesn't work, I'll take off lots of points. So put a sentinel in. And then your queue is also going to use a linked list. So 2 linked lists, 2 sentinels, independent of each other. Okay. So for the stack, we already talked about stacks with linked lists, right? So stack, you have a sentinel node. You push by adding right after the sentinel. And you pop by removing the node right after the sentinel. So you never have to move through your list. You never have to search for the right place to insert because we're not sorting the data. Okay, our insertion order is strictly first in, first out for a stack. So you've got your sentinel node. When you want to insert, make a new node, put it right there after the sentinel. If there was already something there, squeeze it in between. And when you want to pop, take the node after the sentinel, pull that off, point the sentinel to the next node. So all the action happens right there at the sentinel node, which makes this really efficient. And it makes it easier than your add routine from PA2. Okay, linked list implementation of queues we're going to talk about right after this. Unless you're allocating like millions of bytes for your nodes, you're not going to run out of memory. Okay, I'm not going to try pushing a billion things into your stack. So you don't have to worry about memory overflow, basically trying to malloc and running out of space. Otherwise, you have to have some way to pass back an error status, and I don't want to get into that. So don't worry about running out of memory. If you do a malloc and it comes back with null, you can print a message and say, sorry, we're out of memory, goodbye. Okay? But that should not happen, and I won't force that to happen. But if you try to remove from an empty structure, you should print an error message. Popping from an empty queue, popping from an empty stack, removing from an empty queue, print an error message. Keep going, though. Okay, don't exit. Test your code. Make sure you have it well commented. Have a make file to create the executable. Put it all in the tar file. Submit to Canvas by 2 weeks from Friday. All right, basic goals here make sense. Let's look at implementation. I'm fuzzy again. So queue, we want this first in, first out. So we're going to make a linked list. There's a sentinel. And originally this is going to be null. So that's an empty queue. Okay, if we're going to put one thing into the queue, there's really only one way to add something to a list, which is have the sentinel point to it and store whatever is in the data field there and have that be null. So let's say we add a 1. This is what our queue will look like. Okay, now suppose we want to add a 2. There's 2 ways to do this. We can either add that to the beginning of the list or we can add it to the end of the list. And at some level, it makes no difference. We can add it to the beginning and remove from the end, or we can add to the end and remove from the beginning. Right? Shouldn't make any difference, but there's a performance difference that's going to be critical. So option 1 is not what we want to do. So don't do this. So let me see if I can get these right first try. So option 1 will be to add at the beginning and remove at the end, where I'm talking about the beginning and end of the actual list. So this is the beginning, and let's add some nodes. So let's add the number 4. Well, if we want to add, oh, my nodes are backwards here. Okay, if we're adding at the beginning. If I want to add a 4, I need to create a new node and plop it in right here. So I would make a node 4. I'd have this point to my 4, and this would point to the end. How many operations does that take? I don't know, 3 or 4 or 2 maybe. It's a fixed number. It doesn't matter how long the list is. To add something to the beginning of it always takes a small fixed number of operations, because all the magic happens here at the sentinel and the new node. But when I want to remove the first element in the queue, I have to remove from the end of the list. And right now, the only way I can get to the end of the list is to start with the sentinel and move forward until I find a node whose next is null, and then return that. Remember what the previous node was, set that to null. That's an expensive operation. So add is going to be order 1, but remove is going to look like order n, if n is the number of nodes you have in the list. So that's inherently expensive. Now we can try to clean that up by somehow recording what the address of this last node is. So we could have either another variable, or we could add an extra field that we use in the sentinel. And we could use that to say what's the location of the last node. And now when we want to remove, we just follow that. It takes us right to temp. And we can return that data, but we need to somehow back up to the prior node to set this thing's next to null. And we can't do that unless we have a pointer to this node. And so short of making a doubly linked list, this is going to be really expensive. If you do a doubly linked list, it's still order 1, because we can go to the end, we can follow the previous pointer and come back here. But I didn't want to have you do a doubly linked list. Okay, so we're not going to do this approach. It turns out if we do this in the opposite order, it stays very efficient.
If you had like in PA1, we had a valid part of the structure.
Mm-hmm.
We had like a head and a tail. So if you flipped it 1 or 0 every time, this was the head, this was the tail.
Same idea. When we flip if this is the end of the queue, and we're removing this, we need to somehow get to this node so we can flip that flag to say this is the end of the queue. And we still need a pointer back to it. But other than that, yeah, that would work fine.
What if you just have well, never mind. I was thinking if you had a pointer that points to the second to last entry, but then you'd have to change that.
Right.
When you remove to the one before it.
Yeah, so that's why if you do a doubly linked list, you've got pointers to everything before. And then when you remove a node, you've still got a pointer to the second to the last, and so on. But kind of mysteriously, this seems to work. So option 2, this is what you want to do. So add at the end and remove at the beginning. So let's say we added a 1 and a 2 and a 3. So we were adding to the end, so this is going to look like 1, 2, 3. Here's the sentinel. And I'm going to add one field to each of these nodes. I'm not going to use it anywhere except in the sentinel, but I'm going to call this tail pointer. And this is always going to point to the tail of our list. Now, it's not the maintenance that's required for a doubly linked list, because there's nothing here that points to the 2, there's nothing in the 2 that points to the 3. The sentinel simply has a pointer to the first node and another pointer to the last node in the list. Okay, well, removing is easy, right? Removing is just deleting the first node in the list. Doesn't involve anything about the tail, so my tail pointer is never going to have to change. So removing, I just have to say sentinel next equals sentinel next next. So this thing is going to point to the thing that this node was pointing to. And before I can do that, I have to make sure sentinel next is not null. So if this field is null, my list is empty, my queue is empty, I don't remove, right? But assuming that the queue is not empty, then sentinel next is actually a node, and so I just set this thing to point wherever this is pointing. So that's our usual delete function, but we're just deleting the first element. The add is almost as straightforward. So we want to add a number n, so make a new node, set the data field as usual. So here's our new node. So let's add a 4. So set the data field to 4. Well, we can get to the tail immediately. We follow the tail pointer to this node. This is the field we want to set to point to our new node. So we can do something like sentinel tail pointer next equals, let me call this temp. So temp's our new node. So start the sentinel, follow the tail pointer to get to the last node, set its next field to point to temp. Set temp next to be null as usual. And then what's the last thing we have to do? Change the tail pointer. So we need the tail pointer to point to the new tail. And that's just one line. Sentinel tail pointer equals temp. These are the kinds of codes where these pictures are really priceless, right? Because if without the picture, if you try to figure out what those 3 lines of code should be, or at least the first and third, it'll probably be really, really tricky, right? If you draw a picture, I know I want this to point to my last node. Okay, this is sentinel tail pointer should be equal to temp, right? It should kind of fall out at you once you are drawing pictures that map to your code. And this always works, except when your queue is empty. So when your queue is empty, you can't do sentinel tail pointer. I mean, you might set it to null, in which case sentinel tail pointer next will segfault. So before you add to a queue using this approach, you want to know if your queue is empty. If it is, edge case. Make a new node, set sentinel next to point to that node, set sentinel tail pointer to also point to that node. And then the rest of the code is the same. So this is what I coded up last night, and it seems to work. Did not work first try. It didn't work my first few tries. If it makes you feel any better, I took about 20 tries to get it to compile. I had a dog on my lap while I was typing it in, so that was part of it, but still, sometimes you use the compiler to check your syntax. That's fine. All right, does that look doable? So this is totally different from the usual linked list we've been doing in PA2, right? It's still a linked list, but we're using it in a different way, particularly with the queue where we've got this idea of a tail pointer. Now, for development purposes, if you don't want to mess around with this, just go through your queue until you go through your list until you get to the end and deal with it like that. But for the submission, I want to see this tail pointer. Okay, so I put a comment in here, which I already got rid of, unfortunately. But let's look at the other details on this assignment. All right, so for the stack, push new elements by adding a node, etc. For the queue, the head is the node immediately after the sentinel. So let's annotate this. So this is the head. This is the tail. Okay, that's why I call it a tail pointer. So you added the head, which is, sorry, you added the tail, which is right here, you remove from the head. Removal's fast because it's always right next to the sentinel. We've got something pointing to it, and we know what comes after it because we have forward pointers. Adding to the tail is fast because we can get to the tail with the tail pointer, and we know that the node that we add is always going to point to null because it's at the end. So both add and remove will be order 1 operations. All right, so the head is the node immediately after the sentinel. The tail is at the far end of the list. So remove elements by accessing the node immediately after the sentinel, that's the head, and add new elements by adding to the end of the list. And it says in bold, it's important that you do this efficiently. That's the tail pointer. So you should augment your node structure to include a pointer to the end of the list, but you only use that field in the sentinel node. Okay, to keep track of the end of the list. And I want you to do it like this as opposed to making a doubly linked list. Okay, this saves you from having to work to the end by working forward from the beginning. Again, don't travel down the list to find the end, unless you want to do that while you're developing. Okay? But on the final project, I want you to just use the tail pointer and jump straight to the end. And then when you add a new node at the tail, you need to adjust the value of tail pointer in the sentinel. And when you remove from the head, there's no need to deal with the tail pointer because you haven't changed the tail. So how do we know if the queue is empty? Exactly. So if the linked list is empty, the queue is empty. And here again, there's no really rigid definition of a queue being full. It's full if when you try to malloc, you run out of memory. But that's a hard thing to detect. So when you malloc, check the return value so you don't. And if it returns null from malloc, then you're out of memory. Do something. At least print a message. Operation failed out of memory. And keep going. But I have a hard time testing that. So my recommendations, make yourself a Q init, Q add, Q remove, Q empty, and a Q print. And make yourself a stack init, a stack add, and so on. Or if you want, you can make a generic routine that takes an argument that says whether you're doing this to a stack or a queue, provided you're passing the same kind of thing, which is going to be a pointer to an integer. So each of these things, like when you say queue add, you want to pass it your queue and your number. So this is an integer star. Sorry, this is a, well, let's back up here. So we need some structures, right? So these can all be struct nodes, except the queue nodes need to have this tail pointer. But if you want just one kind of node, you can add the tail pointer in the struct nodes that you're using for the stack and just ignore it. That's fair. So you have a struct node. And num's just an int, as usual. Or you can make a queue node and you can make a stack node, or an S node, right? Which may help you keep things straight. It's up to you. It kind of depends how crazy you want to get with setting all of this up. So most of these routines, add, remove, empty, and print, you need to pass the pointer to the sentinel. So call it whatever you like. Could be Q sentinel and S sentinel. It could just be Q and stack. It could be, you know, Barney and Betty or whatever, your favorite. And Q init can be something that just returns a struct node star. So like your init in PA2. And in your main program, you can declare a struct node star named Q and a struct node star named stack. Set stack equal to S init, set Q equal to Q init. And some of these things may do the same thing, but I think it's cleaner to sort of have a separate set of functions for each. That would be my preference.
Is there any way to go to that the last paper that you had?
Mm-hmm.
For a second. So this is for a queue, right?
This is for a queue.
So wouldn't it be 1, 2, 3?
Let's see. I might have gotten it backwards. So, yes, it is.
I was looking over my notes. I'm like,
Yep.
is this queue?
Thank you. Yeah, so add at the end. Yeah, so I tried to do that in my head. I got it wrong. Thanks. So yeah, it would be 1, 2, 3, and then the new node is 4. Thank you. Good catch. Do another picture of that. All right, so organize your code, modularize it however makes sense to you. But I would definitely try to keep an abstract view of stacks and queues in your main program. And then, like I say, if you want the practice, you can try implementing these things with arrays, and you don't have to change your main code, maybe a little bit. Right? Your queue will be an integer pointer instead of a struct node pointer. But your function calls can be the same, and you change the prototypes, and it should all go back together again. Mm-hmm.
That fourth function here,
Say again?
the fourth function you have in that list,
Q empty, yeah.
it's like your is empty function.
Yeah. So that just looks to see if Sentinel's next is null. And I don't really care what you call these things, right? So the things that I'm going to grade you on are pretty much spelled out in here, right? And within reason, if it's not in here, you've got liberty to do things the way you want. But if you're unsure, definitely ask. right? So for example, I don't want you to use a pre-existing stack and queue package, right? Even though I don't explicitly say that in here. So use common sense and ask if there's any doubt. But what you call these functions, do you, have a init return a struct node star, or do you pass an argument and set it inside there? Do you print an error if your queue's full? Do you do something else, right? I'm not really worried about most of those details, so do what's reasonable and ask if you're unsure. But the things I'm going to assess this on are described in the assignment. So I'm looking for basic functional behavior, right? The stuff that we saw when we ran the code, and making sure that you're doing this efficiently. So for the queue, making sure you've got a tail pointer that's saving you from marching through all the elements. And I can't test that. I'm going to look at your code and see what's going on in there. So that's where comments can help too. So how many people comment their code as they're writing it? How many people find commenting to be helpful, at least to some degree? Okay, that's encouraging. I had a note from someone that said they removed their comments while they were writing because it was making the code confusing, and then they didn't have time to put it back in. And I can relate to that in some ways, but I just wondered how common that experience was.
So is it not as smart to do what I do, which is like, okay, it's all done, everything's done, but I'm going to grade it down if I don't have comments, and then go through and add comments to everywhere?
Honestly, that's what most people seem to do, I think.
Oh, okay.
In a school situation. And honestly, when I'm writing code for this class, that tends to be what I find myself doing more often than not. But if I'm writing something that I haven't written before, especially, I'm definitely commenting as I go. And I'm commenting not for somebody else to see, but for me to see. Because I've had enough times where I've worked on code and gone back to it maybe just a few days later, and I have no idea what's going on in this section. And it was something that seemed really clever at the time, and I tried a few different things, and I finally got it to work. But I go back to it, and I'm still thinking of it all the ways that didn't work. And it's cost me so much time in the past that by and large, if it's something that's new to me, or if it's a new approach or something that I'm figuring out, I'll tend to comment as I go. But that's really for my benefit, right? So probably the ideal is some kind of mix of, commenting as you go to let you know what's happening, and then going back and sort of like adding the stuff that you know you need. Like, you don't need to put your name on the top of your code to help you write your code, right? You know who you are, you know what class you're in. So that's purely an add-on so you don't lose points. So it's probably a mix in the end.
I mean, it was helpful because, like, for PA1, 1 and 2 are pretty simple. But
Mm-hmm.
you're changing the pointers, so I was able to copy a lot of that, and then it was helpful for the comments, like, okay, this is going to do this, so I know where I need to
Right.
change here. So that was kind of helpful.
Mm-hmm. And some code is self-documenting, right? When you prototype a function, that basically tells you what you're passing to it. And you can actually put variable names in your prototype, and if you make those names kind of meaningful, you don't necessarily need a comment right there saying, this is a function called add that takes a pointer to a struct node and takes an integer and adds it to the list, right? Because if your function's called add list and it takes a struct node star and an integer, you kind of know that. So yeah, it's a organic process of figuring out what your right level of commenting is, and it's different for each person. And frankly, it's different over time. There's spots where I find myself getting really wordy, and then sometimes it's just like la 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 la, 500 lines, no comments. Did anybody look at that coding style guideline that somebody posted on the discussion? What was your thoughts about that? I'm not judging.
I actually, because I was the one that posted it.
Yeah.
I actually thought it was interesting because while I didn't, agree with every single choice they listed out in the guide. It was kind of helpful to see like examples of what is terrible, or like style at least. Like they were like, don't do this, and they'd have like, you know, half statements on one
Right.
and it's like, well, who would do that?
Yeah.
And then something more subtle like variable naming.
Mm-hmm.
You know? Like,
Don't make it too simple. Don't make it too complex.
yeah, I watched something in the summer where the guy was like, oh, be as descriptive as possible with your variables, so everyone knows what you're talking about, like they read the code. But then in this guide, the guy's like, well, don't say something like the name of the person that makes the music.
Right,
It's
right.
too wordy, and nobody wants to write that.
Yeah.
So,
It also kind of makes you aware of like, there's some things I just don't like for some reason, and like one thing is the bracket right after the function or whatever,
Mm-hmm.
and I don't like that. But you have to realize that wherever you work, they're going to have guidelines, and you shouldn't get too comfortable in your own ways, set in your own ways, because that might change.
Right.
So,
Yeah. You love it?
Yeah.
Yeah.
I like the curly brace right after.
Yeah, I mean, I definitely remember kind of having conversations with myself about where I was going to put that. So, you know, integer fun. I didn't know where I was going to put it until I actually wrote it. I know when I type it, but I couldn't actually like recreate that in my head. So yeah, I put it down here. Some people will put it up here. I think one thing that's useful about looking at a style guide is just to sort of realize the kinds of things that you could choose to be consistent about, like where do I put the brace after a function? And for me, I don't really care if you do this, or if you do, you know, throw a space in there before the curly bracket. And different places may require one of those and not allow the others, right? But to me, if you're being consistent, it's going to help you because I know, for example, how to find where my function starts, right? I can look straight up and look for that.
Yeah, so I don't know about that.
Yeah, and if you do this, I know that I can look for, you know, something in this signature and find the start of a function like that. And as long as you're consistent, it's going to make you more efficient when you're working with your code, right? If you can look at an if statement and immediately see what gets done and what doesn't get done based on that condition because you've indented and you have certain conventions, that's going to help you, right? And that's, to me, the primary goal of developing a coding style, is to make it more efficient for you to read your code, but also to write your code, right? The reason I like indenting by hand is because it reminds me where I am in my nested levels of logic. And I can't program with auto indent turned on because I lose that constant reminder of, you know, I'm 5 levels deep here. Right, I actually find that helpful. It drives other people crazy if they're used to auto indent. And when you use something like Eclipse, which we'll use in 2.23, you can set it up to adjust your code to whatever style you want. And you can use a single keystroke and your whole code changes and it has whatever your style guide says it should look like. So that's always handy. Unless you don't know that that's what it's going to do, and suddenly all your code changes. It's like, whoa.
well, it was funny because somewhere in that guide, it said something that I think you said it was either early this quarter or last quarter, where you can do like if statements don't need brackets if it's one line.
Right.
In the guide, the person points that out, but they're also like, but doing that could cause you to break habit.
Right.
They're like, maybe just go the distance every time. So
Cool.
You just get the habit of it.
Okay, I didn't notice that in there. I took a breeze reading through it, but I didn't notice that one. That's kind of cool.
Well, and then if you go back for, you're like, oh, I need this if statement to do something else. If you didn't have brackets, then, you know.
And that's where I've gotten burned by it, and that's why I always do brackets.
I got burned by it last night.
Yeah? Good stuff. Yeah?
Is the midterm next week?
Oh, I don't know. I was kind of wondering about that. Is it?
It was supposed to be yesterday.
I know it wasn't week 4, but I think it's week 5.
That's what I was thinking too. Are you dipping after this class?
I have office hours right after this, so you can come by. Yeah, let's double check because that means I need to make a midterm. And I think it's week 5, and then 215 is week 6.
I wrote the brain function exactly how it is in class.
Very bad at making the process look good.